buggers. All right, this is the final review. So we have all these resources opened up to talk about stuff. So this is probably going to focus primarily on like chapters 5 and 6 in general. Even though on the actual final, the breakdown is 2 questions per chapter with 2 questions for what, chapter 1, chapter 2, chapter 4, and then 4 questions for 5 and 6, which breaks out to be.
What he specifically said on it was 6 for chapters 1 through 4, meaning there could be any distribution of those, but there's going to be 6 allocated for those 3 chapters.
Yeah.
And then probably 2 per chapter for the 5 and 6. So that's just the exact, terminology he used just to make sure. But probably that's how he's going to do it. Because
And I don't know if this, I don't know how much water this holds, maybe not too much, but I looked on his Rate My Professor just to see what people had said in the past. And I remember someone saying that he reused like chapters 1 through 4 problems from previous exams from that semester on the final. So
I mean, I wouldn't. A lot of professors tend to do that.
yeah.
I would love for him to do that, but he probably will be like, haha, I swapped the sign somewhere to make it negative instead of positive just to jack with them.
Flex. All right. So
can we look at the stuff? Because I don't think he got all the way through this, did he?
He went through everything. He didn't read off the final slide where it just had true false questions, other than he said, oh, these are true false questions. Then that was it.
Okay, gotcha.
And then the rest of the stuff, like anything that doesn't have almost an entire page for the work, he just said, you should know how to do this. This stuff should be tattooed on your body. Blah, blah, blah.
Yeah, a bunch of
Simple
formulas.
math.
Oh, did he post a formula sheet already?
Okay, so yeah, there's going to be 2 formula sheets. There's going to be the one that's built into the test.
And there's this one.
And then the 5-page one that is mostly graphs for the new stuff, and then the old formula sheets.
Yeah.
I'm pretty sure that 5-page one is the
official approved cheat sheet.
Yeah. And that's like it's basically it's our first 2. It's the formula sheets were allowed from the first 2 tests plus the new.
Yeah, have transformers here.
Yep, that's right.
It's exactly the same, and then you just put
diodes
in because why not?
For this stuff, ironically, F equals MA torque. I like that that's here.
Mhm.
I don't think we use any of these except V equals IR.
I think that's a sarcastic comment.
Yeah, we have BJT graphs and formulas to go along with these. And then we have MOSFET graphs and formulas to go along with just graphs and some formulas.
And then at the start of the PDF for the final review or whatever, it has some more stuff on it.
Yeah, this stuff.
Yeah, because that's really, I mean, that's basically all you need.
A lot of the stuff's formula plug and chug in general.
Yeah.
All right.
Yeah, and like I'm working like the homework and example problems. That's pretty much all it is.
Yeah. All right. So here we are. 12 points. Given an N MOSFET operating in the triode region has VDS equal to 50 millivolts and conducts 25 microamps when VGS is equal to 1 volt and 50 microamps for VGS is equal to 1.5 volts. So that is 25 microamps for the VGS 1 volt and 50 microamps for the VGS 1.5 volts. So we have to calculate VT, which, it tells us right here. He gives us the solutions. We can just explain everything around through. So he tells us right here that we're given the triode region, which means we get to use the triode region. This is, what's the D stand for again? Is that
drain current?
Drain current formula. So this goes over here. This is something that we are this is from a formula as well. Or is that a constant? No, it tells us right here. That's what he was telling us. Wait. I think so. Oh, this is all for this? Okay, wild.
Yeah, he gives you like 2 sets of data and you have to divide one into the other to solve for VT.
This is very similar to
yeah, it's convoluted as well. So it looks like, so the question he's asking for is what is VT? And he spits out 2 things. We have half a volt for, I think that's the second data set, and 0.4752 volts for the first data set. Now, where did he pull? Okay, so VT is
What he
within.
did
Well, no,
is-
VT
within
is
here.
constant, but he gives you a drain current, and then I think he gives you a drain
you
to
drain
source
current and a
voltage for
VGS.
each of them.
And
then
he also
so-
gives you the K and
yeah. But
Where'd
when
he
you
give
do
us?
the
Where'd he give
when
us
you-
the KN not here?
part
You
B.
don't.
Part B.
Yeah, but you don't need it for that part A.
Yeah.
It's just
No,
a
it's gonna
ratio
cancel
between
out.
them. Yeah.
Because
So
if
you
look,
basically set up the equation
Mm.
instead of it be for ID, you do it for the K and prime W divide by L. Set it up like that, and then you just set them equal to each other, and then you're good. He doesn't do the math where it's very easy to understand what the heck's going on.
Yeah, he gets to this. So for both of them, he gets to this step here where you have your K naught and W over L or omega over L, whatever,
Yeah.
and he's got that one
And so
here.
you basically set them both to equal that, and then set them equal to each other, and then solve for,
Wait, you're telling you said you're setting both of these to equal to the Kn and then set them equal to each other?
Yeah,
Yeah.
you
Yeah,
can do
that
it
is
that way.
that is what he did.
Yeah.
That's a little weird.
He
he
basically
just
just
divided one to
divided them.
the other.
which works, I guess, but I just, I
Oh,
think
wait a second. This isn't 2. This is approximately 0.5 volts.
Yeah.
there's a typo.
This man.
Oh, VGS1 is put in. Okay.
This man. Okay, I get it
Right,
now.
so
So
then he
this
gives us
is
two
why it was weird.
VGSs, and then we
This
have
is
to
why
find
it was weird to me. So this was just calculating. This is calculating one system. I thought it was doing like with this like 2 different calculations for VT, but no. He just gives us. Okay, so this is actually operating off of a graph. So you're given 2 points on that triode region slope, and we have to calculate the VT.
Right.
So that's how this
Right.
is. Okay, I
And
get
then
it.
so
now.
you set
That's
the
a
two
little stupid.
equations either
Equal to
equal to
this,
each
yeah.
other or divide them into each other, and then you have
Yeah, because then if you
one
set,
unknown.
you set this one equal to Kn, set
Yep.
this one equal to Kn and such, and you're gonna get, 25 divided by 50 to this, and that's what you get
And
here.
then if you already had that set up, then you can just plug and chug the number it gives you in part B, and you're good.
Yeah.
Yeah, because VT is pretty much going to be like for a given like
Mm.
MOSFET.
I mean, in general, I
configuration.
know like the acceptable range for VT, and 0.5 volts is right there.
Yeah, well, I'm just saying it's going to be
Yeah.
constant for like a given MOSFET.
Yeah, if you're getting VTs that are higher than a volt, you should expect VTs within 0.4 to 0.8 volts. Any higher or lower than that is kind of sus, and you probably fucked up. In general, from
Yeah, but
310, because
Test
this-
questions like to just set it to 1.
this isn't quite the same formulas and such that we would use for solid state fundamentals, which is E310, but it's a very similar topic, the MOSFET and BJT stuff that we do in this class. And threshold voltage is a big part of that stuff. But there's a just slightly different formula if I remember correctly. But okay, so that's how they did that. And then for B, they actually give you this, and then it lets you solve for the WL ratio.
Yeah,
So in
what
this
is-
instance, they give Kn is equal to 50 micrograms per volt squared. And ask for so the W over L is denoted as the device aspect ratio, and it just is 20 here.
So what's in his denominator right there for
This?
part B? Yeah.
So this is the denominator here is this portion.
Okay.
He just
So
picked one of them. He picked one of these. It looks like he picked
The 50.
Okay. Yeah.
this
Yeah.
one.
I see.
The green current's 50.
Yeah, and he divided this whole bracketed portion with the VT of 0.475 volts plugged in. You can see that here over to this side, leaving Kn omega L. And
Okay,
then
gotcha,
Kn omega
gotcha.
L's, we have Kn, so you can also divide that over,
Mhm.
which he does at the end once he's calculated
Okay. Gotcha.
this.
Yeah,
And
that
that
makes
results
sense.
in it being 0.05 because it's just multiplying the denominator by Kn omega L, and then you get
Yeah.
your stuff.
Yeah, so the biggest thing for this one then is knowing what equation to use given that you're in the
Luckily,
triode region.
It tells you the triode region,
Yeah.
and this results in spitting out an equation. Let's check out the formula sheet.
It's not going
I think it's on
formula
the.
sheet.
It should be
It's on-
MOS.
It's not going to be in this formula sheet.
Oh yeah, it is. I think this is the one for the. Is this the one for the final exam?
Oh no, it does.
This
it does
is
on the
the-
chart.
It
Yeah.
has a
the
bunch
chart,
of
yeah,
stuff.
the chart. No, like on the chart, it has the formulas right there on the chart.
Yeah,
So that's for the triode region.
it has the
and there's
relationship.
saturation. Okay, I was wrong. I thought they didn't have.
Now,
And then
how do we?
there's
That's the question. How do we read this chart? Is this the one we're
So-
using for triode?
There's a better one
Shading.
too. Scroll up. The one that I think is no. Keep going. I think he's got it.
This looks like
above that.
BJT's.
Well, okay, it's not on that one.
Well, I can look at this and scroll up.
Yeah, that one right there.
That one I love.
That right there. So that's that's the best one to go off of because it separates them. Like if you go down to the bottom of that square, yeah, just right there. So you see where it's split triode and saturation.
No,
and
it just tells you.
And then it also gives you your little inequality that tells you what will
The drain source versus OV.
Mm-hmm.
Drain source greater than. Yeah. Okay. Cool. Yes. All right. That makes sense. In general, that's good to see. So in general, I would actually very much like to see a question like this because this isn't actually that difficult by any means.
Yeah,
this is nice.
Yeah, it's a really straightforward.
Circuits. No one likes to see circuits. You don't know if the MOSFET is in triode or saturation region, so pick a region and see if you guess correctly. All right, for the M MOSFET circuit below, find RD and RS, those being resistors in this circuit, in order to establish a drain current of 0.1 milliamp and a drain voltage of 0.3 volts. MOSFET data is the thermal voltage is 0.5 volts. On Cox is 400 microamps per volt squared. Oh, this is that KN, isn't it?
Mm-hmm.
That's what he calls it? All right, cool.
I think it's mu n COX, which is the same as KN prime.
And just so you know, it's prime. So the KN would just be that time 5 divided by 0.
Yeah, and then we have L's 0.4 microns and W's 5. So that ratio, WL is going to be 5 microns divided by 0.4 microns. Microns is what, 10⁻⁶ meters then, or no?
Yeah.
Micro, yeah, okay, that's what I thought. So that's units of length. Cool.
Yeah, I've seen at least in the book problems thus far, they've used like microamps, or they've used micro, pico, nano, and then femto.
Yeah, so they tend to work within the, increase by 3 rule.
Yeah.
Or decrease by 3, I could say. So looking at this, the main rule of this stuff is picking your test, and that's what his whole thing is here. So that harkens back to this branch, whether it's in the triode or the saturation, and that gives you these two things that are your assumptions that you test once you've done your calculations. So you can use either of these, but in general, it's best to use your DS versus your OV for either of them. So if you assume triode and this equality isn't fulfilled, I'll zoom in. If this equality isn't fulfilled when you test for the triode region, then you are wrong in your assumption and you have to use the saturation region. And same thing. In this instance, for this question, he starts with the saturation and it ends up being correct. And you'll see that he later tests the drain source versus the OV voltage and it's greater than it or equal to it. That also satisfies the system. It's a little too big now. So let's go down here. So assuming saturation, he pulled that formula and he plugged in the information that he was given. We were given ID. We were given K, we were given, mu naught, K naught, whatever, K prime. We were given omega, we were given W, we were given L, plugged in there. We were not given the gate source voltage, which is something we have to calculate, if I'm not mistaken.
Well, it's a means to get to.
Yeah, you're going to need to find them. Yeah, we're going to need it to calculate RD and RS. So we'll have to find that, but then we are given a thermal voltage of 0.5 volts. So the only thing missing here is we're immediately calculating VGS, which we all know how to do algebra. This is pretty basic, 0.7 volts, that's cool. So now over here, we have to go do some, circuit analysis, my favorite thing.
Oh, real quick, I'm pretty sure it's V_t, so I think that's just the startup voltage type of thing.
Threshold, not thermal, you're right.
Threshold, yeah, threshold.
That makes, that's a lot better. Thermal voltage is
I just for the record, I just wanted to make sure.
Let's fix that.
Yeah, and I don't think thermal doesn't show up with, I don't think, any of the MOSFETs.
Yeah, thermal was in solid state fundamentals and diodes.
And also
yeah, I was gonna say it will show up with BJTs.
Yeah. All right, so now that once you've found VGS, this is more of a circuits problem than it is a MOSFET problem. So you're given the MOSFET and stuff, and VGS is the gate source voltage. So that's, what is that, here to here, I believe?
Yes.
So we're also given a positive 1 volt is across RD with an ID across it. And then we have a negative 1 volt across RS with IS across it. And then we have VS and VD, which is the voltage sample taken at these points or these nodes in the circuit. So going through, this is analyzing it from the bottom because we have our negative 1 volt. So this is using, what is this? This isn't Kirchhoff's, right? No, this shit is right. This should be Kirchhoff's law.
Yeah, it is.
All right, so we have a
I'm
negative
just
1
going
volt
up.
going this way, current across RS. So this is solving it with the voltage assumptions. So this is a voltage. This will result in a voltage. This is a voltage equal to 0. So our closed loop here, I guess technically, because this is a ground or whatever source. Either
Yeah.
way, go up through here. We have 1 volt to start. Go across RS is going to have the current IS going across RS. Coolio. And we're solving for RS here. And then we have VGS, which we calculated to be 0.7 volts over here. Plugging everything in IS we have already. Now, why do we have IS already?
Because IS is always equal to ID for a MOSFET.
And
That's the
ID was
same
given
for-
to us, huh?
Mhm.
Nice. All right, let's he doesn't note that here, does he? That's probably a good thing to note. So for everyone at home, IS is equal to ID for MOSFETs. Remember the rules. So knowing that and taking that information, we can plug everything in except for RS, and that's a solve. That's actually pretty basic. And then checking VS, which is the source voltage, which is right here. So this is the node check. We can use that same thing. And it's negative 0.7, which makes sense. Since in general, this is VGS, which was 0.7, as we know, goes to here. So when you measure here and it hasn't gone across the resistor or anything yet, it's still going to be the same voltage, but it is a different polarity.
Yeah, and another thing to do, like rather than having to do the KVL, once you get that VGS is 0.7, since you know that VG is at ground, you can just say VGS equals VG minus VS, solve for VS, and you get negative 0.7. And then you can just, say, what is it? RS is equal to VS minus negative 1 volt over ID and solve it that way.
Yeah. And then down here, going the other direction with a reference of 1 positive volt at the top and using ID, which was given over here at the beginning, which is, 1 milliamp. Why is he doing 10 to the negative 4th if it's 1? Oh, it's 0.1 milliamp. Never mind. That's why. All right. So we're given that information. Go down here and we're solving for VD this time instead. Well, we're not solving for D. We're solving for RV. We have VD already. VD being, in this case, should just be the potential drop across the resistor. Let's see. We have VD plus RD, ID. We have ID. We have negative 1. And then we have 0. So VD is 0.3 here. So I take it that's 1 volt minus the gate source.
It's given to you in the problem as well.
Oh, where's that one? Oh, we have a drain. Oh, POG. Okay, never
And it
mind.
makes sense because VG is going to equal 0 because it's grounded. So if you do the algebra,
All right,
if you already
gotcha.
have the VS, it kind of.
So the VD was given to us in the problem as 0.3, as illustrated where my mouse is. So we're basically given everything we need except for RD, and you just solve for that, and that spits out 7,000 ohms. Now, once you've solved for this, as I said all the way at the beginning, you don't get to say you're right quite yet. You need to confirm that you were right by comparing your DS. Yeah, no, that is DS. I've been reading this as O, but his Ds are just horrible. You have to compare your DS and your GS and your VT here. So if in saturation, then that means DS is greater than the gate source minus the, that's not thermal. That
Threshold
is
voltage.
threshold voltage, yes, all right.
Why can't we just use Ohm's law for solving for RD, because we're given both ID and the resistor, or not the resistor value, but the voltage at that terminal.
I thought that too.
I mean,
and he said because with this sort of thing, we have to use different rules because a device, and so it doesn't always work out how it should normally.
Yeah, so
Okay.
Otherwise, you could, because IS should equal the same as ID, and then you could just this is the current across the resistor, so that's what it should be, but it doesn't work that way.
not quite.
So we can't assume that it's linear.
No.
With that
I
specific
don't think we
thing,
can.
yes, we can.
Yeah, with that. Okay, thank you.
Yeah, so here, our VDS was, is it DS or is it VD here? Either so, I'm pretty sure that it is supposed to be. It's supposed to be 0.3, no, that's VD. where do we pull VDS from? Drain source. So VD's coming in over here.
Well, if you know,
VDS.
yeah, if you know
VDS is the potential
VD,
between them.
So
Yeah, that's all it is.
VDS equals VD minus VS, which not always, but it does for sure equal VDG, like the drain to ground, and then the ground to source. If you subtract DG and GS, you get DS. Which, if you get this, you have 0.3 minus negative 0.7.
It's 1.
Yeah. So that's where he got that from.
And of course, that's bigger than the gate source minus the threshold voltage, which is 0.4. So that fits the assumption here because the DS has to be larger than the GS minus the threshold voltage.
Is he using different, like when he does his KVLs? For that first one solving for RS, is he considering like a voltage increase to be positive, and then
looking at
for
it,
the second one he's considering a voltage drop, like the voltage drop across RD, to be positive?
Yeah, that every once in a while I'm like,
Not that it matters, but
you're
like
allowed to make whatever assumptions you want, I suppose.
Yeah, like scroll just a tad so we can see the top. Okay, so like the first one makes sense because he's going on, okay, voltage rise is how I'm going to go. So he's going up to the right, and then the first one's -1. Okay, that makes sense. And then the other one, he's doing the same thing. What the? Okay. Oh no, that's the same. Okay, I'm stupid.
That's
okay,
part of the same.
those are the same equations. I'm looking at the same ones, and I'm like the logic. Yeah, and then
this
and
one comes down.
Yeah, where the heck did he get the -1 from?
So.
Oh yeah, because he's
yeah,
that makes more sense. Okay. Actually, why is that one negative?
Because I think if you make the loop and you like turned it into a voltage source, maybe like if you drew the whole loop, you might be going from the negative terminal to the positive terminal, which in this case
he could have look. So you see how in this one he starts with 1.
Yeah, -1. Yeah.
In this one he starts with VD, so he's going up like this.
Okay. Okay, that makes more sense.
So the potential across the resistors in the opposite direction. And in this case, he's starting with the 1 volt, and you see that he denotes negative here, so it's plus minus. So this one stays its polarity, and this one flips its polarity because he goes this way. And this one he goes to the 1 volt and goes up over. This one he goes at the VD and goes in up because he ends at VGS here, and in this instance he ends at the 1, so he goes like this.
All right, that makes more sense.
Funny.
Like the math works out. We're just kind of like
it's just sus.
Yeah.
Amogus.
All right.
He doesn't keep consistent, and that's what kind of freaks me out.
All right, BGT time, puggers. All right. For the BGT circuit below, determine the voltages at all nodes and currents in all branches. All right, so we're given a beta, so that means we can solve for alpha if we need to. Which, does he even do that ever? Yes, he does, almost immediately, in fact. And alpha is 0.99 from that. You can see that down later, but either way. We have to find IB, IC, IE, VB, VC, and VE, and he has them labeled on that circuit. I wish the circuit was a little bit bigger.
Yeah.
Wasn't as smushed as it is, but it is what it is. So we're given a VBE in the circuit, it looks like. I don't think he gives it to us in the problem.
Yeah. And he told us if it's not given at all, assume 0.7, since that's just a regular like PN junction.
Yeah, and that's what we got here. So VBE is equal to 0.7. So starting, it looks like this time he starts from the VBE ground node. It's like over here. It comes up. Wait, does he? No, he starts over here.
Well, for this one, we can go ahead. We can basically find, so VE is at ground, right?
Yes.
So we already know that. And since we know VBE, we can find VB, which I'm guessing is it negative 0.7?
Let's look. Just
0.7.
Well, yeah, because
and that's because it doesn't change potential across this.
You're right.
And also it's because it's VB minus VE. That's one of those big things that it's nice because the B and then the E, you know.
So I take it in this instance.
The order you do this, the subtraction.
Yeah.
VE being 0, yeah. So and VC is 1.4 volts. So VC is up here. So we go from 10. Yeah, so he does VC plus 2K, IC minus 10. So he started at VC and went up. So it looks like okay, I think I'm starting to find his pattern though, the way he analyzes these problems. Because he likes to start at these sample nodes and move in a direction, or start at like something down here. So in this instance, for this question, which portion is this? For his IB, he started up here and moved in and went down to the VE branch, which is grounded. So he went over and through. But in this one, he starts at VC and goes up and over. Because he goes VC, then he goes through the 2K with the IC current across it, and then he goes up to the 10, which is every time you go up to a positive in his method of doing things, it always results in a negative voltage. So he does it this way. He's done it twice in two
Yeah,
different.
and that makes more
Gosh.
sense now because from 213, we usually start from a voltage source and then go
Yeah.
across resistors, which are always voltage drops. So he's just multiplying what we're used to doing by negative.
Yeah, but that also sucks because look at the way he's denoted IC, like in the diagram.
It's downward.
As like, yeah, and that's opposite to what he actually did
Yeah.
in the KVL for that. That's
So using this,
so
he actually ended up
insane.
needing beta for this, because beta is equivalent to the IC divided by the IB. So we have IB already, correct?
Mhm.
I think we found it really easy because
Oh
Yeah.
yeah, it's over here.
we could find that since VE was 0, that kind of that made it where
Yeah, it literally drops from 5 volts to 0 across one resistor, so you're
Yeah.
immediately given.
well, and
And-
also across the VBE junction because that's a 0.7 drop as well.
Oh yeah. So
And what-
that's exactly what it does. 5 minus 0.7 divided by 1 OK, 4.3 divided by 1 OK spits out this, and this is your
Yeah, and then now you can find
VBE.
all of them with it.
And
now.
then given beta, which is the rule ratio between IC and IB, 100 times the value of IB spits out an IC, and you're done there. And then here's where he calculates that alpha value, because notice that the relationship between alpha and beta is pretty standard. If you want to find alpha, it's equal to beta over beta plus 1. If you want to find beta, it's equal to alpha over alpha plus 1, if I remember correctly.
No, it's opposite. It's
Minus
It's
1?
Alpha.
It's
over-
1 minus A.
Yeah.
on the
yeah,
bottom.
1 minus A.
Okay.
It's on the formula sheet. Just check it every time.
Let's make sure.
Mhm.
Yeah, there. What?
Right here.
Yeah.
Beta. Okay, so this,
Oh, it is. What the heck? Okay, alpha equal. Oh yeah, no, I was right.
there's a
Okay, so
couple.
That's
There's an extra one.
why is
so-
it beta? Oh, because there's a 1 on top instead.
So
of
alpha is equal to beta over beta plus 1, which is what he used there. Beta is equal to alpha over 1 minus A. And then there's this extra one where if you wanted to solve for this quantity, you could,
yeah.
Don't
but
do that.
I'm probably never going to use that one.
Yeah. Don't
Yeah.
use that.
All right, where were we? We were
Yeah, and that's
going-
what he was saying is like he said a couple times in class is that if you have alpha or beta,
You're
in
basically
any
set.
one current, you can find everything else.
And if you have C and B, you can find beta, which can find alpha.
And then you're set. Yeah, it's just a
Yeah.
chain reaction.
it's
All right.
beautiful.
So understanding his method of analysis of these problems is good to see, because if he particularly likes starting at a VC and going up like this to a source voltage, I mean, I'll do the same thing he does. It's not that difficult to set up an equation doing it this way. So, and that finds you IC. Well, actually, that's not what found him IC. He did that with IB. What is this even for? This just solves for VC, doesn't it? It helps. Yeah, that's what he does. He uses it to solve for VC. All right, that's cool. All right, so that's cool. All right, moving on then. BJT amp, find the voltage gain. Similar to chapter 1 homework problems. Okay. All right, we're given all these initial values, and here's the V out equation. So that's RCGM times, was that V pi? Is that the symbol he wrote there?
Yep.
Yeah.
That's awkward. All right.
It's
Coolio.
in the book. That's why he did it.
I
Because
mean, I don't doubt it.
Yeah, it is in the book this way when they're like saying this is basically the circuit that from chapter 1, except it's a BL, BG.
Hey man, use the BJT to amplify instead of the op amp, bro. Why not? All right. So he immediately, because we were given everything except the V out here, it looks like. Yep. So being given that information, this Oh, and this is wait, V sig? Is that supposed to be
V
no,
you
that's
mean
somewhere
like
else.
V signal
So
is what
Yeah,
he's
yeah, that's
that's
over.
your
He just
input
puts that in
voltage.
over here. So he augments the no, he solves for something here, which is the ratio V out V pi. Wait, did he do it that way or no?
yes.
Yeah.
Okay, yes. And then he uses this number later, and he uses a separate equation here.
Yeah, well, what he's doing, I think, is it's basically, I mean, it's pretty much straight up like a chapter 1 problem where like with current gain or current or voltage gains or whatever, it's like the ratio of the input to the output, because that's that V out over V sig is the
Yeah.
gain for that
So,
amplifier.
out over V sig, which as
Yeah.
V sig's just the input technically. It's just what you're
Yeah.
slapping into the amp.
And then the 2, him solving
So
for V
he does it in
pi
an
is
interesting
just
way though. I
like
like it because you see at the
voltage
end
division.
where he uses the ratios to cancel the V pi and just get the thing. I like that.
Yeah, this is straight up a chapter 1 homework
This is actually really
problem.
so he solves for this ratio and leaves V out over V sig equal to negative 200. He goes and uses this formula to solve for V pi V sig and spits out another number. And then since he gets to set these equal to something, multiply them, cancel that, and then over here all you do is multiply your result and you have a number.
Yeah, that was like the cleanest way he did it. It was
That is pretty clean.
yeah.
Well,
One
it's
page.
just of that first loop, it's just voltage division, right? To
Yeah.
find V pi.
Yeah.
I don't we
Second
don't even
equation.
find V pi. We
Well,
don't
but
even need it.
Well, you do
set
find
it,
V
yeah.
pi. Number 2, right on number 2, you do find the
Well, you
value
find
of
V pi over V sig.
If you
Yeah.
just plugged everything in, you could find it. But
Yeah.
Oh well, I wouldn't do that. Wait, can we even?
yeah,
Yeah, you
because
We don't have V sig. We just have the ratio V out V sig.
no, we do have. Oh yeah.
Yeah, no, we can't
Right.
find V pi in this. The
Oh, no,
reason
he's right.
V pi just gets deleted. We can't
Yeah.
find it in this instance. If
Well,
we had V sig, then we could,
Yeah.
but we don't, unfortunately. But we only need to know this ratio.
So
And this
you
one
get
happens to be negative 193.5. Pog. All right. So this is another whole thing. 20 points.
Well, there are also 5 of them.
Ah, okay. So
Four,
this is asking
sorry,
for the
yeah.
region. What region is the BJT or MOSFET? What is this?
This is the Lord of the Rings quote.
And he says high culture literature. Oh,
Also,
boy.
well, look at the date. Look at the date.
It's from 2007.
It's before the
Oh.
movies freaking came out. I'm
Well,
pretty sure it is before.
in my opinion, we should just have some quotes from the Epic of Gilgamesh, but no, well.
That's too old.
just add another 4,000 years on that. And then you're good. All right. What region is the BHE or MOSFET operating in? No partial credit. Legend. So we have a VC of 4 volts DC, a VB of 2 volts DC, and a V of 5 volts DC. And
By the way,
says
he
that
does
this-
work on the next page, just so you know.
Excellence. All right, we'll work with this page instead because this is kind of pointless. So obviously there have to be rules here somewhere, right?
The main
Whether
thing
it's on the
is
formula sheet or something.
when I watched lectures where he walked through it, the main thing to look at is one. He said he's probably not going to have a question set like this, but it's good practice because you will have to kind of do the same sort of thought process. For the first thing you need to do is it a PNP or NPN? Because that's going to be the big thing of like which things you add and subtract and all that.
Well, PNP versus MPN is simply the direction, right, of this little
Yeah.
arrow.
Yeah.
Yeah,
exactly.
but you
So
gotta
this
think-
is an MPN. This is standard, and this is PNP. It's the opposite.
But like you see, they have the same voltages, but literally the opposite value
Yeah, so it flips them.
or answer or whatever.
Nuts. Yeah, so let's see. We have our in, our gate, and then we have our out. So what is it? We have, does anyone remember the real name for these? We have the collector, the emitter,
and the base.
and the base. Yeah, all right. I had to memorize that because I use BJTs all the time like a gremlin. Let's see. So we have 5 volts plus VBE, which is the potential across, from E to B here. Funny enough. I like how they flip it when it's going E to B, either way. -2, which in this case is the voltage on the P portion or the base, is equal to 0. Therefore, VBE is equal to -3 RB. Okay, cool.
There's also a chart that's in the book that if they're both reverse bias, it's cutoff. If they're both forward bias, it's saturation. There's a fourth one that I can't remember,
So why, for what
you-
reason, is this
It's-
reverse bias because it's negative? No.
Yes. If
Oh,
it's
it is?
negative, it's reverse bias.
And then for
So what about this one? This one doesn't, is not negative. It's positive and it says reverse bias. Oh, but that's being taken from the opposite side, isn't
yeah,
it?
Yeah.
So, okay.
So
So double
technically,
reverse is cut off?
technically, yeah, double reverse is cut off. And
the
then
other region is active.
It's saturation, cutoff, and active for BJT and triode for MOSFET.
and technically there's a fourth one. But he said no one uses it, so don't worry about it. Like it was in the PDF. I mean, not the PDF.
The
slideshow.
mythical fourth state.
Yeah, I'll pull it up just for the fun of it.
Mythical fourth state of matter that every 5-year-old, when they learn about it, feels like a genius.
Pretty sure it's reverse active.
Well, that sounds
Yeah,
fun.
reverse active.
So
There-
reverse active is what? It's active in the opposite direction it's supposed to be?
okay, so one. Okay, so
Excellent.
that one's if it's one's forward biased and the one's reverse biased. So it's one the combination. So 50-50. You're. I don't remember. I might have a screenshot of the textbook.
Sounds like
Fine.
pain. All right. Now the MOSFET, we have a VD is equal to 2, VG equal to 0, and we have a VS equal to 1. So VG we are given, VGS, which is GS is the potential difference here, is going to be equal to, well, we solve for that in a second, but I can already tell you that this is going to be equal to -1 just looking at it. If you go from 0 to 1 and it's positive to negative, then you flip and it's -1. And that's exactly what they calculate here.
Mhm.
But
Oh,
in
by
this
the
case,
way, real quick.
Mm.
If it is reverse biased on the CB junction or BC junction, depending on which one it is. If it's reverse on that, and on the EB forward, then it's active.
what did you just say? Let's get that again.
Okay, BJTs.
Mm.
It is an active if it is forward biased on the EB junction,
Okay.
and it is reverse biased on the CB junction.
And that's active.
Yes,
Okay.
and if it was
And saturation is FB, FB, and cutoff is RB, RB.
Yep. And then the mythical one that reverse, what was it? Who someone said it like 10 seconds ago.
Reverse
Yeah,
active.
reverse active.
Reverse active. That one's the swap of it.
So that would be reverse on the EB and forward on the CB.
Correct.
Okay, fun. Oh, and we didn't look at this one, but it's in saturation. So all you need to know for saturation is they're both in forward bias, going from across your VB to going from your collector to your base and then your base to your emitter. As long as they're both FB, you're chilling. And
So-
remember, for the second portion, FB is negative, right? Because you're
Yeah, that's how he does it in
in this instance, if it's
in the
positive,
book,
then it's
and
reversed.
how they talk about it. What you do is you just straight up subtract the voltages from each other.
Mm.
So like VBC is for the P and P, I believe, and
Yeah.
so you subtract it B minus C.
Yeah, and for the test, I've seen stuff that someone said that he wants us to email him which modality we intend to take the test in. Should we actually do that, or should we just assume that?
I'm doing
Doesn't
it because I haven't seen a Canvas thing posted, and I'm like paranoid that I'm gonna wake up that day and be like not able to take the test yet, and then get a 0 on it. It was like, oh, you took the test late.
Yeah, well, I guess everyone should then respect his wishes and email him,
Yeah.
inform him of the modality you intend to take it in.
So when you subtract, so doing it the other way that you were mentioning, do you just
For
subtract the,
BJTs,
yeah. Well,
Mm.
or for
Okay.
MOSFETs, for either
MOSFETs have
one.
different rules.
Yeah, it does. Now,
It's-
okay, on A, if you see on A how he said VBE, and then if you
Right.
go over to B, it says VEB, so it swaps the order of the B and the E. Okay.
Yeah, but
So the order in which the letters are, and that's how you do the subtraction versus, based upon the PNP or NP.
So,
Sorry,
but-
go ahead.
yeah. So either way, though, you're just subtracting the positive terminal from the negative terminal. I mean, that's
Yeah,
Technically,
basically,
yeah.
thing.
yeah, essentially. So in terms of polarity, yeah, it's the same thing. But in terms of if you don't want to redraw it and put in the polarity of the exact, the negative and plus and stuff sign, and you just want to do the algebra real quick, that's how you do it.
Okay, thanks.
All right, but yeah, all the way it's just different way of skins a cat.
In these in these instances, finding your cutoff saturation or active region for your BJTs is definitely more annoying than the MOSFETs.
For sure.
The MOSFETs, you just have to see, you don't need to do two different equations, you just do one thing.
Yeah.
And this looks like it's assuming that the threshold voltage is 1.
Yeah, if you go up to the top, it tells that the threshold voltage is 1 on both.
Yeah, it just
Yeah, you're
gives
right.
it to us.
And so these are the same thing. I think.
Yeah,
Except
so in this
you have
instance,
to change the ground
you
voltage.
have a VG of 0, a VD of 2, and a VS of 1. You only need to find the VGS for this MOSFET. So you immediately go 0 across this drop to 1. So you know that's just going to be -1. You can already know that immediately without even doing this math. But doing the math, VG minus VGS minus 1, you solve that and it's just going to end up being, VG, which is 0. It's going to be subtracted, all that stuff, magic, and it's just going to be VGS is equal to -1, which is a cutoff because for the MOSFET, if it's negative, or more accurately, if VGS is less than your threshold voltage, then it's in cutoff region, right? Because you're cut off because it's the MOSFET's not on. If it's not higher than the
Yeah,
threshold,
it is a door now.
thing's not turned on, so it's not going to do anything. So that's your cutoff region. So that's just, if your gate source is less than your threshold, nothing's going to happen. So it's in cutoff region. Let's go down to D. In this instance, we have a VD is equal to 2, VG is equal to 4, and VS is equal to 2. So you have a voltage drop of 2 volts here. So the VGS is 2. Was I right there?
Yes.
Yes, I was. So you don't even need to do this math. You can just literally in your head subtract VG minus VS to get your VS potential drop. And then
Yeah.
doing that, 2 VGS is greater than 1 in this instance. Threshold is 1, so this thing's on. But the thing
Well,
is, there's another
The
test
reason
case.
why he does it that way is because in a lot of ways you're actually, as you see in the right, you're actually supposed to do DS.
Yeah.
And you can't just do D minus S. You have to do DG and then GS
Yeah,
to
there are
then
different
find it.
rules for that
Yeah.
portion. Because
Though
now we
it-
have to test which region's in. So it's not in cutoff. When it's in
Mhm.
cutoff for MOSFET, that's fun because you just write cutoff. There's no extra
Yeah.
test.
And then you have
But
to
in
do
this
DS.
instance, you have to tell if it's in triode or saturation, right? Yeah.
Correct.
Oh, too far. So we're in D right now. So now we're going to VS plus VDS minus 2. So VD is 2, VS is 2. What they do here? Oh wait, VDS is different. So VS plus VDS and this minus 2, if I had to take a wild guess, is the end actually. Where do they get the minus 2 from? Is that just this?
That's the KVL, yeah.
Yeah, okay. Equal to 0. So then they plug in the 2 for the VS, minus 2, and then they say the drain source equal to 0, because,
I think actually the -2 might be the DG because I know that's a rise of 2. Maybe it's GS that's the drop of 2.
that would make sense. So that's what I would assume. That's where I thought it was coming from,
Yeah, it's just funky.
because that's the only other place I could see a 2 coming from. Either way, so we have a VS, which is given as 2, a -2. These are obviously going to cancel. Then we have VDS equal to 0. Does VDS greater than VGS minus VT? In this instance, this quantity is equal to 1. Is 0 greater than or equal to 1? No. So that collapses us to the triode state if it fulfills this. And I'm pretty sure these rules are given to us on the formula sheet.
Yeah, they are in that table right there.
This allows you to select between the triode and
Yeah,
saturation.
for the MOSFETs, that one table is literally all you're pretty much gonna need, at least. And then I don't know, does he give us the one for the PMOS? Is it slightly different?
No, he said we're not doing PMOSs.
Yeah,
Okay.
PMOS are cringe.
Like he literally showed us, like this thing exists. We're not using it.
Nobody uses PMOS.
Like he's like, this is how you do that. This is what the symbol is. Like literally the only difference between symbol. Like if you scroll up just a tad real quick.
Oh,
Right.
this looks
Yeah.
excellent. This looks excellent.
Like, do you see the arrow on the a little bit above? Like it's scroll up. Like do you see how the arrow points out? Like it
Yeah,
literally
yeah. It's
opposite.
just going in on the other side.
Yeah, and I don't think I've seen a single like homework problem. No, I saw one homework problem that said PMOS. Sorry.
Ew.
And I think it wasn't even one of the ones we were assigned. So I just was like, no.
Can't catch me dead working on a PMOS. All right, find the DCQ points for the circuit. So DCQ points are defined by IDQ, VCEQ, and IBQ. So where do they put it? It's this potential across. This is what, a BJT? Yeah. And then we have the current ICQ up here, and then we have IEQ here. So we have our collector over here, we have our base here, and we have our emitter over here.
Yeah, so it's
EQ is
literally
the
just
potential
your
between our collector and emitter, and then IBQ is the current into the base. Okay, and we're given a bunch of numbers. Let's see. So he immediately reduced this to just the BJT itself. We took this circuit, because this is all ground nodes, and reduced it to this. We were given beta, right? Okay, cool. So he used beta, calculated alpha immediately. IBQ is equal to, yeah, so the ICQ ratio with beta. So he had to get that from somewhere. Now beta, we were given that. Were we given any of the currents? No, so he calculated the currents from one of these things over here. So he calculated RBB, which is
just your equivalent
R1
resistance.
and R2, yeah.
And they did voltage division, which I just sometimes these voltage divisions are not super gosh darn obvious, and it's kind of sketchy how he pulls them out.
So for his RBB, his equivalent resistance, is that just, what rule did he use to calculate the equivalent resistance?
That's literally the parallel.
Oh, so
Yeah.
he did in
It's
parallel.
just it's
okay.
just the different one, instead of it being 1 over that plus 1
Yeah.
over the other one, and then get
I
inverse.
think this is the thing he's talked about with that, like this is what he refers to as like in his lectures, that Mills standard bias circuit or whatever, and basically says you should start by looking left from like your base, take your Thevenin equivalent, which is basically what he's done here with RBB.
And then he also
it just-
uses that RBB to solve VBB of 1.79.
And he did, and did he write it in? Yeah. Oh yeah, he did. He did do VB and VBE, which is nice. Instead of us just going, oh yeah, it's 0.7, he just said no, it is 0.7. You're okay.
Nice. All right. So from that, he then does some Kirchhoff Pog. So IEQ. Do we even have an EQ? We have a
Okay,
CQ,
so
we have a BQ. So technically EQ should be down here, right?
And as you see, he drops the Q like right off the bat.
Come on, man.
Yeah, like it's literally like the book never mentions Q points for
All
any
right.
of this stuff.
This is
The
just
ever.
Q points, okay, when you think about it, and
It's your-
I spent a lot of time today with the Q points. All they are just, this is the point that we want it to operate at.
Yeah, it's your operating conditions for the circuit.
So there's like really no reason for him to say, he could have literally just reset and said, find these 3 and just be ID,
Yeah.
ICE, I'm sorry, VCE and BE, and
Yeah.
we would find
So
it.
using this, so he's starting over here. So we're given RE, which is 400 ohms, but he gave it in kilo ohms because why not? So 400 ohms times IEQ, which is actually IE, and then we do. Oh, he's going in, ain't he? Yeah, because we immediately reached the BE of 0.7. Yeah, he's going this way. He's doing the bottom loop this way, in the opposite to polarity. Because then he reaches RBB IBQ over here, and then he drops by VBB.
Well, real quick, look at the equivalent circuit he did on the right.
This?
Yeah, that's what he's going off of.
That runs a lot better because that talks about his output input loop that he said that he suggests us to do. So that's the output loop, I assume.
So this is him going up to the ground and across this way to VBB. So this line. He goes in from the ground, up across, through, and up. And this is where he gets this equation, where he can then, do quick maths and solve everything using alpha over here. So this is a portion of RBB IBQ. No, this is the EQ. But what?
Okay, so he converted IBQ into IEQ using the laws.
Yeah, because
Did he?
Yes.
Did he mean to write C? I don't
Okay,
think
well,
we have a relationship here.
if you look, so he's all over the place. The math makes sense, but the way he's written it does not. Because if you see, like, toward the bottom of the page, he solves and gets a value for ICQ and then goes back up and plugs that in to find IBQ.
I see.
It's just in a terrible order.
Okay, so essentially he talked about how he got that, but essentially instead of using alpha, there's some other thing he used. Instead of using beta, he used some other thing that's 1 minus alpha that's basically equivalent to it. And that's where he got the 1 minus alpha times IE. It's really funky. Like you
And
honestly, instead of that, like go up all the because we want to convert IB to IE. So essentially it's however you want to do it. So yeah, scroll up just a little bit, I think. Shoot.
Well, this is just the relationships between
Oh,
alpha and beta.
it's that table 6.2. That's what we're looking at.
Okay, yeah. So yeah, zoom in because
Oh, yeah, I see this. So this is an
Blind.
important table too.
yeah, so as you can see, do you see the one where it says IE and then IB like right there? Yeah, right there.
So there's another hidden rule.
It's
There's
like
one up here too.
no, look right. Yeah, it's right above there. Yeah,
Okay,
that's actually
that's it.
exactly what it is. Where
Yeah, he does 1 minus A times IE is equivalent to IB. So that's where he
Yeah.
did.
yeah, so that's where that little check mark thing is. We're like, yes, I
125.
approve this.
All right, that's
Okay.
cool. Memorize that, everybody.
Well, you can do it the other way. It just
I
takes.
mean, theoretically we're supposed to be given that information, so it is. So that's how he solved this. So
Yeah,
I'm pretty
he
sure
did-
that's everything. Once you know that, everything else kind of falls into place. Because he reduces the circuit from this to this and just solves up this way. And then once you have that, you can use this relationship here to this relationship here to solve for CQ without even having to do a branch through.
And then I think the only other thing to look at is how he solved for
CEQ.
VCEQ, which is that last line. Yeah, this last
VCEQ
couple
is
lines.
10 volts, which is up here. So he does do here. So 10 goes that reference of 4.32 volts. We lose. That's RBB or is that VBB? Where do you put it? He
VBB
calculated
is at like the
179.
tone.
VBB is 179. So he got this 4.32 and 0.872 volts from somewhere.
I believe it's from the KVL. Like, look right above it. Like right a little bit. Yeah, right there. Look at that equation. So they have the two. So it's the 2K ohm times the ICR, which is where I think he got that. There's other that other
So we have
stuff.
400 ohms times this is IC 2.8.
No, that's 1.8. So that's IE. That's IE.
That's-
ICIE has it.
That's IE. Then we have CEQ, which is what we're solving for. 2000 ohms times 2.16 micro milliamps,
That's IB.
which is B. And then we have 10 volts, which is the reference up here.
Okay,
is
so
equal to
that's
0.
he's just doing a KVL around that whole.
Yeah,
like,
he's
big
going like
output
this.
loop.
So it's kind of it's weird. You can use the normal Ohm's law to find leftover voltages, but you can't just go, oh yes, this is the voltages across a resistor, and then you can find the current from there. It's kind of weird.
It's excellent. It is flawless.
Sure.
We're all getting 100s on this exam. Mark my words. All right. Find the voltage gain. One of these again. Nuts. We have to find Rn though, and R out as well. And we get to assume stuff. My favorite. So yet again, we reduce this into an op-amp circuit at some point. Or I should say expand since it's bigger. But BJT POG. Oh, we have to do the CQ stuff here. Q points, poggers. All right. We're given beta is equal to 100, VCC is equal to 12 volts DC, VB is equal to 0.7 volts, RC is equal to 6 kilo ohms, RB is equal to 50 kilo ohms, VBB is equal to 1.2 volts DC, VA is 100 volts, and VT is equal to 0.025 volts.
Hey, you know what that VT is?
Is that the thermal here?
That's thermal voltage
Yeah.
this time, yeah.
And
Pog, finally.
also the fact that that VA that corresponds to like an early voltage, I think is what it's called.
Yep.
And that means we're gonna have that like lowercase r sub o.
And if you look a little
Well,
bit
it shows
lower-
up right here,
Yeah.
and it lets you calculate IC. Wait, yes.
Well, no. You have to find IC.
No, you use it to calculate R0 or R naught. Yeah, we get IC from, well, we got a ratio. IC is from up here, isn't it?
So he finds IB and they use beta to find IC.
The alpha relationship. So he finds IB by going through, starts here, he goes across this, and then he goes down across the 0.02. Yeah, so he goes here to ground. So he goes up through and down. So he goes from the base to the emitter and to the ground node. So he goes from 1.2 across 50, which is 50K times IB, and then has a drop of 0.7 volts here and then hits 0, and then he solves there. So that's not too tricky. And then as you said, he uses the relationship with beta to solve IC, which is just 1 milliamp. And then he takes ICQ or IC and solves for GM, the ratio GM, and rho or R0.
And then you can then find R
And then
pi
you can
because
find
you have
this.
E not, and you just fell.
Are those given on that same formula sheet?
Which these ratios, these things?
Those equations, yeah.
Let's
It
look.
might be on the big formula sheet. I don't know for sure.
I think it's on that, maybe on that table 6.2 as well.
Not quite.
No, it must be on the final one then, I guess. I'd be wrong.
I'll look.
Yeah, let's double check.
Yep, right
Yeah,
there.
Yeah,
there
right
it
here for
is.
BJT. Yep. There we are.
And there's one up there for R pi where there's like 2 different ways of doing it.
Beta GM, yeah, and
Thermal voltage.
well, that's a different one, isn't it? That's RC or some shit.
RE? I don't know.
That
Did you
looks more like
zoom
an
in
E.
like all the way?
That's an E.
The heck?
I don't know. We're never using that. I don't know what that is.
Let's just pray it's not going to come up.
I don't think it will.
Like, golly.
Did we go too far?
You overshot my dude, comrade.
This is where we were. Wait.
Yes.
Yep. All right. So we had discussed this. That's easy peasy. IC comes from just rolling one boop, boop, boop. That's just doing that loop. That's no problem. And now we're down here to solve for BE, I guess. You got to draw out this big doodle figure. We have this. No, we're solving for this. We don't have VBE yet. We have GM now, though. We have R pi. We still don't have VBE. We also don't have R in yet, I don't think, because that's one of the things we have to solve for. Unless we already do, we might. But let's see. VBE is equal to R pi over 50K plus R pi times the VSig. We don't know what VSig is. Then we have the 2500, which is R pi. Then we have 52,000, which is given to us previous, I believe. Actually, no, 52K. No, this is just him reducing this. This is the same function. Okay. So we have R pi on the top, and then we have 50K, which is given here, plus R pi on the bottom, 52.5K times VSig, which is 0.048 VSig. We'll use this later, I'm sure, because that's VBE. R out, which is over here, is equivalent to, how's this, R0 parallel with RC, it looks like? Yep, okay, so we do 2500 in parallel with 6000. I would have just, done the math there instead of doodle some lines, but it's not my call, I suppose. And this results in 1,765 ohms. What is that even saying?
Or 6,000 if RO not considered.
Oh.
But it's there, so.
Yeah, so we got to deal with it.
considered.
So that solves for R out. So we have already solved for BE with respect to.
Were we given RC? I can't remember. In the problem
RC?
statement. Okay, yeah,
Yes.
cool.
Yeah, so we have to solve for the input. We have to solve for the voltage gain, which we did. We have to solve for the input resistance, the output resistance, and that's it. So it's 3 things. So this VBE is what results in that voltage. No, it's not. We use that later. We do that whole thing where we eliminate one of the voltages and have V out over VSig, and it turns out this time it's going to be BE. But in this case, R out is 1765. V out, which is what we need to do to get this next ratio, is negative GM times the parallel of R naught and RC once more times VBE. So we've already solved for GM, which is 0.04, it looks like, times this parallel, which we solved for previous, which is equivalent to R out, times VBE, which is equivalent to 0.48 VSig. But in this instance, they leave it in VBE terms. Because then they can do this number divided by VBE. So you have V0 divided by VBE is equal to negative 70.6. And then AV is equal to V0 over VBE, which is negative 70.6, times VBE over VSIG, which is over here, will result in negative 70.6 times 0.048 is equal to 3.3 volts per volt as our gain, because we get to eliminate VB. So yet another clean elimination from what I can tell.
Should that be negative
It should be, actually.
0.38 volts?
I think it should.
Yeah. So this is basically like
It's very
a-
similar to the problem we
it's-
did previous.
yeah, it's a chapter 6 problem through
This thing.
like finding RO and R like V pi or whatever. All
I
that
think these are
crap
literally the
is.
same problem, except this time it makes us calculate the R out and the R in. This time it just doesn't tell it, doesn't ask for it, or it gives it to us. But in this question, it wants extra work because we need to calculate the resistance in and out.
Mhm.
Yeah, because it wants R out and R in.
Oh, that's the next problem. That's a MOSFET.
Oh yeah,
one.
poggers. Yeah, it wants R out and R in over here. All right, moving down. This one also wants us to find the voltage gain, the input resistance, and the output resistance for the circuit. This time we're using a MOSFET, which this circuit just looks painful, right?
Yes.
But, you know, he uses some wizardry and simply immediately reduces it to an op-amp looking thing.
Basically, also, like he talked about this for a long time in class,
Mm.
but the gist is that for like in practicality, those capacitors that are there are important, but in analyzing the problem, they don't matter.
Well, initially it looks like he just says it's infinity on them.
Yeah.
Infinite capacitance, gamers. That's what I'm talking about. Just creative voltage.
There'll be no ripple.
There will be no ripple in my circuit because there will be no current in my circuit. Easy. All right. Let's see. So I would like to know how he reduces it. So let's see. VT
Alright.
is given. That's fine. This is given as well to us. This, you know, KNWL. IDQ, which in this instance is down through this branch, which this is fine because this branch is this is the, what are they for the MOSFET? They're not the same as BGT.
Drain.
Drain, so that's the drain, which makes sense. I drain Q. So that's fine. So this resistance matters. VA coming in is 100 volts, so that's just given. We don't get to, I guess that's just.
VA is the startup voltage. You can't actually analyze it. You just have it there because then.
So
then
he
the
didn't give it
little
to
R
us, so I take it we just assume it.
If it's not given to us, it doesn't exist. If it is given to us, then there is an RO that we have to find.
Okay, and that's from those relationships that we saw earlier.
Exactly.
Also, ignore where it says the find equivalent circuit. See figure 4.43, page 307. That's outdated because
Wrong page.
page 307 is not even in chapter 5.
Alpha. All right, so we've found where the DQ comes from, and that's up here. Why does he get to say it's 1 milliamp immediately?
He just decided to.
But I want to know why he said it though.
Is that just given?
I
Yeah.
guess these have to be givens,
All
right?
right,
I think everything up there
everything
is
the right's
given.
Yeah, I guess okay, these are givens, so we don't have to consider where they come from. They just are. So give this information. This big scary circuit reduces quite quickly. We have an R sig, which is equivalent to the R in this instance. RG. We have
Actually,
the actual.
it's not.
gate.
It's
not.
not.
What is it
He's gonna do equivalent circuits on both sides for those values.
for R sig and R in? These aren't the same.
Because look at RN. That, yeah.
RN is RG.
It's RG.
Yeah,
Well,
not
what's the value
RSig.
of RG? I could have sworn it was given.
It's yeah, it's the same
RG.
thing.
Yeah, they are the same one. So RG is the same. Do we even use RSig anywhere? RSig isn't given. I think he just wrote it because he can, honestly. I don't think it.
I think you Oh wait, no.
Oh, it's
That's
right
something else,
here.
never
I know
mind.
where it is.
You
Yeah.
just said
Yeah,
it's
yeah, yeah, yeah.
100K. So let's look. Yeah, R sig's given right here in the circuit.
And then look, RG. Okay, RG. Look, go back up. Do you see that 10 mega ohms and the 5 mega ohms?
So this is the
That's
RG,
That's RG, I believe.
and these are taken in parallel, and that spits out
Yeah,
3.33.
and that is what RN will turn into, and R sig stays on its own.
Yeah. So RG. So the R resistance in for these circuits for MOSFETs is taken as the parallel branch before you reach. This is gate now, right? Instead of being base.
Yes.
Yeah. Okay. And then this is source.
Now
Gate,
what?
gate source.
Now later on, you'll it took me a little bit to figure it out. So because I thought that was like if you look at the equivalent circuit, at the right side, where you see that RO, and then what it looks like also another RO, but it's
Nah,
actually
it's RD, bro.
Yeah, it's actually RD. So
Nah.
it's just that 7.5K ohms and that 3K ohm on the bottom that goes to
This is RD.
yes.
Well,
And
RD
that-
is the parallel. No, this is RD.
Yeah. You don't do the 3K ohm thing doesn't exist anymore. Like it doesn't show up ever again in the map.
Yes, because this magic capacitor just grounds us.
And it's grounded itself.
Excellent day. All right, so let's look at this. So he uses that GM relationship. We were given this already. What is this? Let's zoom in real close on
That's
that.
VGS minus VT. Which
Yeah,
VGS
This
is
is?
here given.
voltage.
Yeah.
Yeah, it's
Okay.
your overdrive voltage.
Okay. That looked like, I
He
don't know.
does the math like literally 2 centimeters to the right.
Yeah, so this was given, and then, 2 minus 1 is 1. So it's just 0.002 amps per volt. So that's that. Now solving for R0 using that funny little equation, which is VA divided by ID. ID was given to us at the beginning, right up here. Well, IDQ was, but even so. ID was given, so 100 divided by this is 100K. We've solved for R0. RG, which as we discussed, is the parallel of the input resistances on the gate, which when you do parallel 10 mega ohms and 5 mega ohms, it spits out 3.3 mega ohms. And it just so happens that RG in this instance is equivalent to the resistance in. So far we've solved for one of the parameters needed.
And
Next.
real quick, the
Hey.
arrow pointing for RN is on the original circuit as well.
Also, that GM
Yeah.
where he gets the equation for that, I don't know if it's given in the problem or anything, but
I think the GM equation is from the formula sheet.
yeah, I was gonna say I didn't know if it was on there because it's just a random equation 5.9 in the textbook.
Yeah. Well, we'll check after we go through. We've found RN already. Now the next step is solving for the ratio from gate voltage to signal voltage, because it looks like for every single one of these problems when we're doing the gain, we're deleting something. And in this case, we're deleting the GS. So VGS over V sig is equal to RG over RG plus R sig, which is 3.3 over 3.3 plus 100K is really close. So it's just 0.97. And now we need to solve for the other portion of the AV. Wait a second. This is 7K. R out is 7K. 7.5. Why did we lose that? If you solve for a different, oh, it's over here. You do R0 in parallel with RD and you get almost 7K. All right, I get that. So solving for V0 over VGS, which is the second portion of the voltage gain, is negative GM times these 3 resistors in parallel. So R naught, RD, RD,
Yes.
and then R load, RL, or RL. This isn't the same as R out, correct? Or is it? We'll find out in a sec.
R out is RO and RD in parallel.
Yeah, so looking at this, then where did RL come from?
Wait, RN's just RG. Hold on. Oh, RN.
RN is RG.
talking about
R out's over here.
Yeah, there he is. There it is. It's just
Yeah.
just RO and RD.
But I want to know here, because for this portion, they have, I understand we're GM, we calculated that already, but then RO, we could technically reverse,
Well, because we're doing voltage across the overall.
this
Yeah.
whole thing. But here's the thing, where's RL from? We're not given it, right? Oh, we
That's
are, never
just your
mind.
load resistance at the
It
end.
was given, it's 10 kilo ohms. I was just
Yeah.
being derpy of where it is. Okay, well, now you just do parallel of these 3 resistances, R0, RD, and RL. We have those values, doing them parallel, not too tricky, spits out 0.822. this beautiful relationship where you just get to multiply this ratio with this ratio will spit out a -8, which is hot. That's nice. I like it. Deletes that stupid decimal. And then down here, this relationship is reinforced, and this one down here, R out is just R not in parallel with RD.
So is that, if
Approximate
you go
step.
back up to the figure, is his little, like, the little arrow he drew there that says R out by it, in the equivalent circuit he drew? Yeah, that right there. Is that just we're supposed to magically know that that's
So when
that
he
just
draws
means
this,
R
I
out
guess-
and RD together?
yeah, so I guess this means the reason he draws this is so you don't consider RL as part of the resistance out, right? Because it's not part of the resistance out. That's part
And
of the
then-
separate system. This could
and
be
then
taken
this-
away.
And then the same with the R sig for RN.
Yeah, R sig is not
Gotcha.
considered a part of RN. It's considered part of this ratio. That's where it's
Yeah.
used. But this one's
And
RN.
did we talk about why the 3K ohm resistor at the bottom just goes poof?
Does he say anything about it?
I don't remember him saying
I
anything.
don't think he says anything about it, but at the same time, if this is the R out,
Yeah, exactly.
then obviously it goes poof because we don't care about it.
So I assume that if he had the arrow for R out extended all the way down, we would include that
Extended
3K.
down, or if he instead had the R out arrows on this capacitor branch instead.
Yes.
But then of course we would have a different current to consider. We'd have in this case that'd be ISQ, and it would be going
That'd be
to
something
some.
completely different.
it'd be
Okay,
go-
I
it'd
just
be going
wanted to
in
make
some
sure
direction.
that logic with where the
Yeah, but here's the
out-
thing: if this were extended and it were like R out like this, that would be like, I don't think that's even a thing,
Yeah.
because this is coming in and this is going out, so it wouldn't even make sense. I don't
It'll
even
be on
think
the
that's-
test though now.
It'll be on the test now. That's what I like to see.
All
All right, given the circuit below, find voltage VDS and drain current ID. So this is just a bunch of MOSFET equations, ain't it?
This is where we get to quadratic equation.
Is this the one that requires the quadratic? I
Ugh.
see a square. I see a square. Yep, there it is. Excellent. All right. So let's look. He assumes saturation. So it looks like in these questions, we have to assume either, saturation, cutoffs. Well, no, this is assuming saturation or triode, right? We're not assuming cutoff. So we have to figure out whether or not it's triode or a saturation. So to begin, we're given some stuff. Km prime WL is equal to that. So we're given lambda is equal to 0, which we always assume. And we're given our threshold voltage of 1 volt and some other stuff. So we're given this wild looking figure. So with MOSFETs, as we know at this point, these parallel branch things that you have before you reach your gate is your equivalent resistance in that you can use later. And what is it? Resistance out is based on one of the branches, but I don't think we'll have to use that here. So first step is to solve for ID. No, he just sets ID up. And then he plugs in values. We're given this VGS, we were given VT, but that's that. So now we have this, and then by KVL, it looks like he's just solving for IS here, and he proves that IS is equal to ID.
I think he wrote that in because he's like, this is something you have to remember. IS
Yeah.
equals ID. I think he's
No, so it just is.
Yeah, because there's no actual proper current loss.
Okay. So he redraw. This is some convoluted maths. Ba, 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 ba. He just slaps GS in there somewhere. So that comes from 6K IS. IS is equal to ID. Did we solve for ID yet?
Okay,
No.
that
He uses
GS
ID.
at the top and the 5 arrow ID.
Mm,
That is just up there for no reason. He never.
This means nothing, right?
Yeah, like just kill
So
it.
I'm thinking I think I'm seeing where he gets his VGSs from. So he uses this formula to get ID equal to VGS in some way, and then he uses this to plug in places.
And so
I see the number
instead
5
of-
here.
Yeah, well, that's from look over to the left. So he did an
This?
equivalent circuit. No, a little bit down.
Mm,
Yeah, like right there. Do you see the 5 volts across? That's
Oh,
where the 5 volts
beautiful.
come from. So essentially, he did voltage division to figure out what the voltage is across just that resistor, the one that's grounded, and then isolate.
Okay.
which is
So we're given this circuit. Okay, so it's from the 10 volts up here. That's where he's getting these
yeah.
fives.
And
the reason
so
it's like that is because we have two equal valued resistors.
yeah, and so if you do the math for it, it works out. Or
Yeah,
if
I
you
get it.
just try to do the general voltage division equation, when as you know the 10 volts being the source, and then whatever across R2 is the unknown, just swap them around to figure that out. And
Perfection.
yeah, so that's where that came from.
Nice. All right. So doing voltage division, we get these fives. So that's across the resistance. So knowing the voltage across that, we can say the 6K we just know what this is equal to now, because it's given to us over here.
Yeah.
And then we use this relationship for ID to plug in VGSs where needed. So we have 5 minus VGS minus 6K ID, which ID, right, as I said previous, you can plug that in and get another VGS term, which is what he does here. You know, solve, 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 solve. And now you have a quadratic. And you do all of this to just get it into a quadratic, and then you use this formula, and then you're done, because the quadratic just spits out a number, right?
Two numbers.
And obviously, you pick one, right? But does it really matter which one he picks? Does it have to be positive?
Okay, this is what he said, I think, during the lecture, is if you assumed saturation, what value should it be?
So it's gotta be positive.
So yeah, so if you were silly and decided I'm going to do it in cutoff region, which you can't do.
You're not allowed to. You got to pick triode or
Exactly. You got triode, it might come out different. I don't know exactly what I think.
just assume saturation every time.
Assume saturation until you're proven wrong. It's the easiest one to work with. So you just
Yeah.
work with which voltage would work.
Yes. And obviously must be positive for that to function proper.
Yeah.
And all
Or-
right, so this actually isn't that bad.
Or if they're both positive, the one that's greater than VT.
Yeah, I
Were
would
we
say the
also supposed
most
to solve for VDS.
what he solves for up here, VDS with the relationship. So he solves for ID now that he has VGS, and then takes ID and solves for VDS there.
Where does
Oh.
he?
So you get GS down here, right, from the quadratic, takes this
Right.
VGS, and remember, all the way up here, we have a formula that equates
Right,
ID
right.
to VGS, and then we take that formula and it spits out this number when you plug all the numbers in. And then you take this, and VDS is equal to 10 minus 12K ohms times ID, and that's from up here, because we have 10 volts across a 6K ohm. Wait. Oh,
Yeah.
look, it's because ID goes through both. Because ID
Yeah,
is
it's
equal to
the
IS.
series.
So it's through
it's
12
the
12K
voltage.
ohms total. Yeah. So you go down because you go from 10 volts to ground. So a voltage drop of 10.
Mhm.
It just goes from 10 to 0. So 10 down, down.
Well, it's not a voltage drop of 10, but
Hey, it goes from 10 to 0.
well, okay.
Either way, VDS itself
At the end of the day,
ends
yeah.
up being 4 volts. So that would be from this node to this node. So we burn however many volts in each of these resistors.
Oh, I thought you were talking about some other section of it. Never mind. Okay.
No, I'm just saying from 10 to ground. You just lose
from
10 volts
10 to
somewhere.
the ground. Yeah, of course it's gonna
Yeah, you gotta lose them somewhere.
be.
All right, now we're down. to
Those were the
this.
hardest parts, by the way. I'm pretty sure that like, if you don't mind
This
just scrolling,
quadratic.
actually I'll just do it. I'm pretty sure those are the most convoluted ones that just get. Oh nope, number 9 is a little convoluted, but nothing too crazy.
Ooh, charts? Build table? Build Lego City. All right, let's see.
Hey,
Given an N MOSFET with, Cox is O femtofarads and Kn prime, and he gives us W, gives us L. Kn already includes Cox, assume saturation. So he gives us our threshold, he gives us our ID, and I want to operate this MOSFET in the saturation, so he tells us what to assume. And then he says find VGS and then find VOV, which is what? VGS minus
VT.
VT. Okay, cool. So we already have half of that. So we just need to find VGS and we're set. So we're given the saturation formula, which we are given on our formula sheet, and then we start plugging in what we know. So we're 100 microamps is ID, so that starts on the left, half of 194, so Kn primes plug them right there. We were given W and L, so plug those in. This is pretty standard solve.
This is straight up because I mean, if you
just
can do
spits-
the last two MOSFET problems, this
Yeah.
one's cake.
This just spits out a number. There's
Yeah.
nothing special here.
because you're even on this one, you don't have to do the inequality to figure out what region you're in.
Yeah, it just straight tells you. So
capitalizes
here's something that's
saturation
interesting because
region.
so you find VGS, in this line right here. Divide this quantity over here. Take the square root of the quantities on both sides, add 0.7 to this quantity, and then VGS is there, and that's what you have. But then over here, he says VGS minus VT squared is equal to this number. So, this is what he did. Oh, look what he
Because you're
did!
looking for
Look at this!
VOV.
Look at this
Mhm.
legend. So what he did was he just said, did you know that VGS minus VT is equal to VOV? So he actually did part B before part A.
It's beautiful.
Legend. Okay, so that's cool. Because then you take VOV and subtract 0.7 to get VGS. That's alpha, first off. But even so. So that's
And-
nothing too
And
special.
the table gives the equations for both regions, like with the VGS minus VT, and also the equation with the VOV. So
Yeah, so it gives us everything.
yeah.
So in this instance, this is like free points. Like that should be a free multiple choice question if it were to show up.
I hope it shows up.
Nah, our luck, we're getting the quadratic one. And we're getting this thing.
Yeah, except R out's gonna be the entire circuit.
Yeah, it's just gonna be like, R out is this. He's just gonna circle
It's
it.
a big circle.
He's like, good luck. All right. So number 9, given the following operating characteristics of an NMOSFET below and the desired operating Q points are back. Sketch the design space. So what even is that?
So he spent 45 minutes talking about this on the lecture.
I really hope this doesn't show up because I am at a loss.
I
Looking at
think
this thing.
so. What he gave, I think what was probably given was like the 4 VGS lines,
Wait, yeah.
and then you have to draw in.
I think he drew the load line or
and you draw.
This is
that
the load line,
other-
right? This straight one?
Yeah. And then that other
And he
what
marked
is
the
it?
Q point.
Parabolic line.
The
Alright.
what? This?
Yeah.
So,
Over-
okay, so the curved line.
Yeah. So if
You're
I remember,
given-
yeah, go ahead.
Okay, so you're given the current and the voltage and then the max power. And so you just set up a table in part A to find the curve. That's your first operation curve, okay?
Mm,
So that's you draw that first. And then
yes.
you figure out from normal stuff what underneath this curve can I work in? And you want to, of course, work not in cutoff, the non-saturation. So it needs to be above or on that first VGS equals +1 voltage. So it wants to be there.
Well, our
That's
Q
the-
point ends up on VGS +2.
Yeah, I'm saying it needs that's the lower bound.
Okay, so-
We're making our box first.
Gotcha.
And then we figure out which areas are saturation. See that dotted line that has the triode region to the top left of it?
Yeah.
You identify what the triode region is, can't go there. So he said, now all you do is you need to find a nice spot. Now he didn't notice this in the lecture, but can you scroll up just a tad for the question?
Fuck.
Yeah, it says, given the following operation characteristics of the in MOSFET below, meaning the in MOSFET hit circuit that he wrote up, like he drew down there that has the 8 input voltage
Yeah, I
and all
see
that
it.
crap, that would actually be given. He said, oh, I just made the number up. He's like, for
Okay.
engineers, figure out a good number, which he's right, but also, yeah.
Excellent.
So that's given to us. So what we're really thinking of, okay, so we want to find a nice Q point that kind of, operates in that area, which what he did is he found where it lines up with 6, which is below the 8 that of the circuit that is given.
Mhm.
And it looks like it lines up with 3 milliamps just right. And it's on a curve, exactly on a VGS curve. So that's why he picked that Q point. You make your box and you see, where do I want it to be, because I want to work out this problem nicely.
All right.
So
So to build the table in A, did he just say find values of ID and VDS that will give you a
He gave us
max
this
power
information. So this
of-
is the design space, this whole sketch thing. So given this information, you build this table.
right?
based
But that's
off
what
of
I'm saying
making-
is did he just pick, because your power is not
That stays
even on
constant.
the table anywhere.
It just stays
well, what he
constant.
said is just start putting in numbers that make sense. So
Right, so
where's
that's
the what is still in an operational area that's non-cutoff voltage. That's the highest voltage you can do, the lowest current. We put that number in, which if you look at it, it intercepts with a VGS equals 1 volt.
Yeah. So
That's
what he
pretty
so what's good here is you can see what he did. So we were given the information ID max 12 milliamps, VDS max 18 volts, all that stuff, right? So doing that, you could technically, this line that he drew, you can use this information to get a linear formula.
No,
that
It's
produces this.
curved. That's the curved line. The
Oh, that's
curved line.
this.
Yep.
Yeah, I thought so too. And I'm like, oh, that's just a load line. Nope, it's the curved line because I started doing it. It's a polynomial. And also, you will always talk about it as a curve because, well, it's a freaking curve.
And the line for ID is the load line, right? When it in part B.
Yeah, the
'cause that's
thing in
just
B
why it
that
was
he
in,
has
like,
the ID
50.
equals negative VDS. Yeah, that's the
Yeah.
load line.
And he just uses that from the drawing there. Basically does a KVL. Solves
And
the ID.
I pulled up Desmoto, whatever the online thing, for graphing, and that's exactly what the load line is with the resistance value he found.
Okay. And then B is standard. It's just the relationship of ID with the resistances. And then C is actually solving for the resistances.
And all those numbers came from the circuit to the left,
Excellent. Yeah, including
which
this
would be
equation.
provided. You don't have to make that, even though the
Yeah.
lecture said he had to make it. But in the thing it says,
That'd be
given
pretty wild.
circuit given below. He's like, oh yeah, just make it up, and everyone's like, ah.
Then we have for the BJT circuit below. This is another one. This one looks ridiculous, but it actually looks pretty standard.
That's where they just
'Cause
like,
when you see
carbon
this, you have your
RGB.
RN, and we have a VC node, so I can already tell he's gonna go like, huh, and then he's gonna go like, huh. All right, so yeah, he does a Thevenin voltage, which comes from here, which is exactly what he does. He does a 50K minus 150K, which is the parallel, right? Wait, not parallel per se, but it's
It's the Thevenin equivalent. So what you do is you
50
take
divided by 100 plus 50.
It's basically a form of voltage division. Okay. Because what you're doing is you're finding the voltage across the smaller ohm one. All right. And you take the smaller ohm resistance.
And technically, in this instance, wouldn't it be you find it across 100 and then drop what's right here? Because that's going in.
Well, I guess I don't know exactly.
You could find it here too if you wanted. I mean,
Yeah.
you'd have the same information. This would be 10 volts across here or something.
It's not really equivalent resistance on that section for finding V Thevenin. It's just voltage division.
Yeah. All right.
I think you'll find the actual R value, but you can't.
Our Thevenin's over here. Yeah.
Yeah, you can't use R Thevenin to get V Thevenin with this, but you just have to find them individually.
Going down here, he gives us a beta, so that's cool. So he immediately rearranges this, and then he also solves for alpha as well. And yeah, okay, that's standard looking. And then IE is equal to IC alpha, so we know this one too, because this is also an equation that's given. So he just immediately solves for ratio stuff to use later when he finally gets one of the currents.
Well,
and then he gets the base.
Does it a little bit less linearly, but he erased like his arrows and stuff with how he did stuff.
Well, then down here he solves for his base current, which is, what's coming into this thing.
And note with that is 0.01 times 10 to the negative third milliamps.
So it's actually in microamps.
Microamps.
Yeah, so it's really just in microamps.
Okay, interesting method of denoting that. And then, so where did he solve for the base is what I'm looking for.
Okay, so base, he just did, he doesn't actually show it directly, but if you see the equation, right there. Yeah, he used that. Now, if you plug the value in for IC that he found, for that, you'll actually get an answer a little bit off. He rounded up by quite a bit.
So he found IC over here?
Well, down. Right there.
Oh, yeah. He uses that formula.
Yeah, he just drug down the equation. Now, I love that he has one line that's fully written out, and then he just stops, and then he rewrites the same line, but with a coefficient that actually works.
Yeah, down over here. And then he goes that, and then obviously once you have IC, which you can use this equation to immediately find IB, hop over here, find I is equal to IB plus IC, checkmate. And then VCE 4.5, and VC 8.5, which he did that.
Yeah, scroll down. There's a duplicate. Scroll down more.
Oh,
And then there he finds them. Yep.
this?
Yep.
So he just does more Kirchhoff and then nothing special here. So let's see where he's, okay. Yeah. He really likes rounding, huh?
Yeah, his rounding kind of.
A little tricky sometimes. Is this? It's like the last portion. So let's see. An N MOSFET with threshold voltage VT equals 1 volt is to be operated with following voltages. So we have a source voltage of 0, a gate voltage of positive 2.5 volts, and a drain voltage of 1 volt. What is the gate to source voltage? Well, it's 2.5. Because, if you go, 2.5 minus 0 is still 2.5. What is the overdrive voltage, which is GS minus VT? VT is given to us as 1 volt. So, 2.5 minus 1 is 1.5. Done. What is the drain voltage? It drain source voltage, but it gives us the drain voltage of 1 volt positive, and then it gives us a source voltage of 0. So if you're going to go from one to the other, 1 minus 0 is 1. So checkmate. Then we do D. What is the region of the operation for the N MOSFET triode, saturation, or cutoff? So it's asking you to test which is which. So if drain source is greater than OV, overdrive, and it's greater than gate source minus the threshold voltage, it's saturation. So working that out, it's not in saturation that he just did there when you check all of those inequalities, because you're going to have DS is equal to 1, which is already immediately proven incorrectly, because GS, which is 2.5 minus VT, which is 1, is equal to 1.5. 1 is not greater than or equal to 1.5, so it's not in the saturation mode. Now, technically, if you're confident it's not in cutoff, which you can test for cutoff first if you'd like, but let's look here, just make sure it's not in cutoff. It doesn't look like it because there's no reverse bias. Your drain source is positive. Oh wait, no. Cutoff is just if the GS isn't greater than your VT, right?
Yep.
Okay. Well, we know that too. So you can already know it's not in cutoff. So you don't even need to test the triode here. Technically, you can just, if you test saturation, you can say it's in triode. But for testing purposes, your drain source has to be less than your overdrive voltage for it to be in the triode state. 1 is less than 1.5, so it's in the triode state in this instance. Problem 7, this is BJT looking magic stuff. Pog. BJT has very large beta and assume VBE 0.7 volts. Find VC, which is up here, which if you actually carry this through is actually over here. Wait, is it actually? That's the problem. He didn't note if this is a node or if this is a parallel wire skip. Like he doesn't denote if these are connected. Should we assume they're connected?
What I'm thinking is the node is like the VC is a node right at that junction.
Yeah,
I
that's-
do
that's
think
what
that
I-
it is.
That would make
too.
more sense, I guess. All right, let's back off. So VC, and then it's also asking for the emitter current, which is coming out over here. So he says beta is equal to ICIB, but we know that, beta is very large. So he says IB must be very small then, right? So therefore negligent or neglect, he says. So that just says we get to say IC is equal to only IE, which I guess makes sense. So you use your KVL. So if you're starting at -10 here with KVL, that means you started here, goes up through here with IE across the 3K, goes across the VBE break, goes across the 9.1K. Oh, so he didn't go across. So he went across the VBE, but he didn't go into the base. He went up through and he went up to the collector instead. Goes across this resistance and then goes to 10 volts. So actually he starts with a negative voltage, which is technically taken as a positive reference here. So your sign doesn't change. And then he goes up to 10 volts, which the sign changes. So you end up with 2 -10s. Excellent. So doing this and using this magical IE is equal to IC, you can use this to just immediately solve for IE. So this equation right here, reduce it down, replace. VBE was given as 0.7, so he plugged that in. He replaces IC with IE, so just solve, and then he says 1.5 milliamps. So now we also know IC because they are identical. And using this information, we can solve for VC, which in this case, he starts here and goes, right? So they are connected. So technically, even if it were connected here, it could be connected here, it doesn't matter. It's all connected. So you just go whop. This time he went up through this branch and broke past through the 10K ohm. Wait, did he even do
Wait,
that?
no, he doesn't.
No, he doesn't. He
Yeah.
just goes right here and stops.
Yeah.
Okay, yeah, he just stops.
So wait, so he has taken into account the voltage drop between B and E, but what about
You're just given that. You're
between-
just given that.
right, but like, wouldn't there be a one between C and E as well to consider?
Technically, but I don't think we need to care about it.
They have it labeled like
They label it,
Yeah.
but
there, but I
but
don't
he's
think
asking
no.
for VC, right? So we know, we know VE, right? Because it's,
Yeah.
negative 10 volts or whatever. And we're calculating VC. So in theory, we could calculate VC,
Oh, okay.
but we
Well,
don't need to.
okay, I see. Sorry, I was talking about, shouldn't we be caring about the voltage drop between C and B, but there isn't one.
Nah, I
There
mean,
isn't
not only is that like, because we're not going that way anyways. And these technically, in reality, when you use a BJT like this, you have current coming this way and current going this way, and it all comes out the emitter.
So
Right, but what
looks-
he's doing is he's jumping the junction. So he's saying like negative 10 across the 3K ohm resistor, then across the PN junction between VBE. But then you've got another PN junction between C and B, but there's no voltage drop between those, right?
Magic, right?
And is that because they're both connected to VC?
I suppose, since
Yeah.
you have one, because this is technically taken as a node, so, VC is the correct voltage here and here. So that's fun. So now we have some true falses, right? Always got to remember these, not that they matter, because I don't think they show up anymore.
They're
True
good.
false.
Well, or there might just be one that's worth 10 points.
Excellent. All right.
That was like I knew it because it was on the project, but it was still the most gut-wrenching 50-50 ever.
I'm still mad that I lost a single point on my project submission.
Ow.
I'm enraged.
Did he even like tell you what it was or no?
I didn't look at it.
He's like, I'm mad. I don't want to bother with this.
Exactly. All right. True, false. For MOSFETs in saturation region, drain current is equal to source current. So this is DS. So this is yes. So the drain is equal to source. So whatever. So it's just you don't lose any current across it when it's in saturation. Then in B, for N MOSFETs, the gate voltage must always be less than the threshold voltage. Otherwise, the MOSFET is. This is false because the gate voltage has to be higher than the threshold for it to do anything. And it is false. If it's not higher than the threshold voltage, the MOSFET is, in fact, dumb as a fence post. Also known as not on. C, for BJTs, alpha is very nearly 1, and the base current is always less than the emitter and collector. This is correct. Whenever you calculate from beta, alpha is almost always just like 0.97 or something. And then just in principle, if you've ever used a BJT transistor, the base current is always less than the emitter and collector currents. Now, could you dump more current into the base if you wanted to? Yeah. Should you? No. It'll just break. The whole point of a transistor in the first place is to use small signals with small currents to control bigger stuff. It's basically a relay, right? So it's a relay with extra sauce, right? So you really shouldn't have to dump more power into your base in order to make the thing work. So always put a 10K ohm resistor on your base and put like a 1K ohm resistor on your collector. That's what I do with my BJTs. And then I proceed to give them the same voltage. All right. D, true, false. For BJTs, the Q points are determined by VDS, ID, and VG. So this is false. Can anyone explain why this is false? Because I don't remember Q points well enough.
All right, so VDS, ID, VG. Okay, go up to the thing where we had to do the problem. That you know what I'm talking about. Nope, up where there's actually a chart. Yeah, yep, yep. Okay, so where the heck is VG? Exactly. There's no
That's
VG. There's VGS.
Well, did it say that said for a BJT, not a MOSFET, right?
I think it's the same situation almost though.
I wonder though. Wait, scroll back to the true false.
That might be the question because there's no. Yeah.
Yep.
Yep. Because
think
there's the G's there because a G doesn't need to be there, and there.
Yeah. And there's none of those are part of a BJT. Those are all MOSFET Q points. So I think
I get it. It's all a gotcha question.
Yep. Yep.
All right, cool. Of course, he just slaps, problem 8 after 9. Why not? And then problem 9 after 8. Magic.
Listen, he literally just like took screenshots of other tests after scanning them and
That's
just
what I
like
wanna know.
minced them together.
Okay, so he gives us this one's
And
nice as heck. Look, he
this
gives
is
us
super
gives
easy.
us alpha and says, "Give me beta," which I'm sure you just use the magic numbers and it spits out 199. Then you got to find the IE emitter current. So you know that IC is equal to alpha IE, and it gave you IC, so you just do that, and then you got to find your base current, which yet another relationship, IC via beta is related to IB. You do that, and it spits out that number, and you're done. Hey, look, the base current is a whole 3 orders of magnitude smaller than the emitter current.
Wow.
All right. All right, 10 possible points for these true false. Get it? Let's do it. For BJT, if you know alpha or beta and one other current, you can find the other 2 BGA currents. This is true. We literally just did that. B, for a MOSFET, if VGS does not exceed the threshold voltage, the MOSFET remains dumb as a fence post. Yes, this is true. If the gate is less than the threshold, the thing won't turn on. So it is in
I
fact
love that he
stupid.
said so true.
I love it. Sometimes he's just shit posting and it's awesome.
I freaking like it.
All right, so part C, the best place to operate a MOSFET is along the boundary line between the triad and the saturation regions. Stay away from the boundary line. Anyone have a reason as to why? Because I don't.
Well, okay, the boundary line for that essentially means. Wait, hold on.
It's where is it where VDS is equal
This would be the boundary line, this dot, right?
All right, so essentially it will fidget between operating in triode and saturation.
Yeah.
And so you're basically, your battery's going to change, nothing's perfect. So it's just going to ping pong between being operating in triode and in saturation region because it's never going to stay perfectly on that line. It's
That's
just
no fun.
not going to be consistent with its operation.
Yeah,
and I think mathematically that's the point where VDS is equal to VOV?
Yeah, because if you look at the correlations of saturation zone and triode region, they actually have a question in the homework, I believe, where you have that and you get to choose which one is the same value and you can prove that they're the same values, doing both equations at that specific point with that specific BJT. So essentially, yes, there is a region where you can the equations equal each other.
Icky.
Yeah, that's why I said don't use it.
Yeah.
No kinks.
All right, so that's why it's false. It's not the best place. It is in fact the worst place. All right. D. Oh, Zener diode? A Zener diode must be operated in forward bias in order to obtain the regulated Zener. The whole thing, Zener diodes must be used in reverse bias. So this is false, obviously. E. An ideal amplifier has a finite impedance or input impedance and an infinite output impedance. Huh. Infinite output. Yeah, that's hella useful. False. Nah, that's useless. Hit me with an infinite output resistance, I'd rather be dead.
I'm very glad that he writes the correct answers or what they should be.
Yeah, for some of them, but for that one, I'm pretty sure we all know that part.
Oh yeah.
Hope.
Yeah,
And same with the Zener. I'm so mad we didn't get to use like gun diodes or tunnel diodes because those things are just ridiculous.
All right, Mr. I'm overqualified for this class. Okay, problem 10. You should all know this.
I don't think he gives this is the end of the file. Though.
Yeah, there's not really a problem here. He just says, I want information system designed to use ideal op amps that will give me V out is equal to this polynomial, right? So we're used to doing this. So it's just the weighted summer.
Yep.
And in this instance, it's literally one, as you said previous before this started, it's one op amp because they're all positive, right?
Okay, so if you guys remember the question that we had the same thing like this on test 1.
Yes.
So with that one, the solution he gave was he had 3 op amps, 2 feeding into 1, the first one dealing with the ones that have positive coefficients, and the other one with negative coefficients. The one that has negative coefficients in the final output have positive input voltages. So if let's say that the V1 had a negative coefficient, it would just be V1 going into it. And then for the negative ones is the other way around. So essentially for this, we would just do one amplifier, set up, input voltages of 1, 2, and 3, have them set to negative, and then do some funky dunky easy math to figure out the
to find the
resistance values.
ratios
And
of the
then
resistances.
exactly, and then that's it. It's literally a third of one of our homework problems.
Excellent. Nice.
Do
Yeah,
you
we
want
didn't,
to-
look. We didn't even have to look at these things. This is
do
just
you
what
want-
he
yeah.
did.
Do we want to
Oh, she
skim?
has this. If we wanted to look at something like this, she has her own like practice test problem thing. But these look relatively. This looks interesting, but I don't think we're gonna have to deal with this. But
Yeah.
that is a homework problem type thing.
Mhm.
yeah.
All right, fellas, I got to get out of here.
All right.
Best of luck on the final.
Everyone's gonna get an 100. I'm telling you right now.
Now,
Hope so.
now, question: do we want to skim through the past test or no?
Probably not. So what is it? Thursday?
Yeah.
I think it's better for us to like we just did what we did. So this is almost a 2-hour session. So this reaches like
heck
the
yeah,
limit.
let's leave. We're
Yeah.
done.
So
Never
even
mind,
so,
finish it.
so I'm gonna stop recording in general. But normally.